Welcome back to our channel. Today's class I am going to discuss about the classification of digital systems in VLSI design. Before entering the topic, first I recall the term digital system. So what is system? So system in the sense it's a collection of components that incorporate in a single board or single chip. It's called as a system. So digital is the one type of signal, either logic 0 or logic 1. This signal is applied to the system. The system doing some operation and finally release the output. So it's called as a digital system. So this video I fully focus how the signal is classified in digital systems. So classification of digital system. So in digital system, the signal can be classified depending on how they are related to a local clock. So how they are related to local clock. So based on that, we classified into four types. So among these four types, the three type is classified based on predetermined period in time. So signals that transition only at predetermined period in time can be classified as synchronous, mesocronous, and plisocronous with respect to system clock. The next classification is asynchronous, a signal that can transition at arbitrary time. The signal that can transition at arbitrary time is considered a synchronous signal. So totally in digital system, the signal is classified into four types. First one is synchronous, second one mesocronous, third one plisocronous, and final one asynchronous. So just to look at this diagram, the graphical representation of synchronous, mesocronous, and plisocronous is shown in the figure. We will discuss one by one. The first classification is synchronous interconnect. So synchronous interconnect in the sense that the common clock frequency is applied to entire block. So it's called as a synchronous circuit. A synchronous signal is one that has the exact same frequency. Exact same frequency is applied to different block and now fixed phase offset. So fixed phase offset with respect to the local clock. So this synchronous timing methodology, the signal is synchronized with the clock. So whenever the clock frequency is hitting in the register, so that time only the register getting the data and sample the data. So the data can be sampled directly without any uncertainty. So after hitting the clock pulse, directly getting the data and sample the data. In synchronous system or the most straightforward type of interconnect. So it's a straightforward type of interconnect where the flow of data in a circuit proceeds in lockstep with the system clock shown below. So this is the simple structure for synchronous interconnect methodology. So in this diagram, we have two registers and one common clock. So this CLK represent clock, IN represent input value, R1 and R2 is the register. So the R1 register is getting the input data from input after hitting the clock pulse. So when the clock pulse is applied to R1, so this R1 register is getting the data and sample the data. So after sampling, the output is given to combinational logic. So that output is namely called as CA. So this combinational logic block doing some operation, then the result is applied to input of R2 register. So after getting the clock pulse, this R2 register getting the data from here, C out value, then sample the data. So after sampling, it will produce the output. The length of uncertainty period or the period where data is not valid. So after giving the clock pulse, there is no output in the output side. So this period is called as the uncertainty period. Then come to mesocronous interconnect. So it's a graphical representation of a pulse. A mesocronous also signal. So this signal has the same frequency, but an unknown phase offset. So unknown phase offset with respect to local clock. So for example, I'm taking two different clock pulse. The data is being passed between the two different clock domains. So transmitted block is different clock, and receiver module, it has a different clock pulse. The data is traveled between the transmitter side to different module side, receiver module side. So in such system, it is not possible to directly sample the output at the receiving module, because transmitter side different clock pulse and receiver side different clock pulse. It's a block diagram for isochronous communication approach using variable delay line. So in this diagram, we have two blocks that namely called as block A and block B. So block A considered as a transmitter, block B considered as receiver. So TR and RX. So TR represent transmitter, RX represent receiver. So in this transmitter block, applying the different clock pulse, clock A, and clock B is applied to receiver block on register R2. So this block A, it holding the data. So after getting the clock pulse, this data is given to R1 register. So after getting the clock pulse, this R1 register is sampled the data, input data. So after sampling, the data is passed to interconnect delay. So this interconnect delay block is mainly used to synchronize the transmitter block and receiver block. So after delay, the data is passed to D2. So this block is called as a variable delay. So this block also used to aligning the delay between the transmitter and receiver. So clock signal is applied to block B and R2. So after getting the clock pulse, this R2 register getting the data. So this D3 is applied to R2. So after getting the clock pulse, R2 register sample the data. After sampling, the data is passed to input of block B, then receive the data. So PD is the delay controller. So this is the basic operation of a isochronous communication approach. Then come to isochronous. So in this isochronous interconnect, so it's also one signal. So this signal is normally same, but slightly different frequency as the local clock. So here, when two interacting modules have independent clock generated from separate crystal oscillator. So in this isochronous interconnect module, we have a two modules, so transmitter and receiver. So both are having different clock frequencies. That frequency is generated by two different crystal oscillators. So the signal is transmitted from transmitter, then the receiver is receiving the signal. So it's a simple block diagram for a isochronous interconnect. Here, so this is the originating module, so transmitter module. This one is the receiving module. So these two modules are having different clock pulse. So this clock pulse is generated by different crystal oscillator. So this is the clock C1. This is the clock C2. So C1 is applied to originating module. C2 is applying to receiving module. So timing recovery. So this block is mainly used to synchronize the originating module and receiving module data. So this timing recovery is send the signal to FIFO. So FIFO in the sense first in, first out. So C3 is the enable signal for FIFO. So after getting the C3 value, the FIFO buffer getting the data from originating module. Then this data is transferred to receiving module. So this is the operation of isochronous interconnect. Then come to asynchronous interconnect. So asynchronous signal can transition at any arbitrary time and are not slaved to any local clock. So synchronous interconnect in the sense common clock frequency is applied to every block, and asynchronous in the sense individual clock pulse is applied to the blocks. So as a result, it is not a straightforward. So synchronous is a straightforward to sample the data, but asynchronous interconnect is not straightforward to map this arbitrary transition into a synchronous data stream. So although it is possible to synchronize asynchronous signal by detecting event and introducing latencies into a data stream synchronized to local clock. So handle asynchronous signal is to simplify, eliminate use of local clock and utilize self-timed asynchronous design approach. So this is the interconnection block diagram. So in this block diagram, we have a 2 register and self-timed logic. So it's one module, it's another module. So this is the input data. So this input data is supplied to register. So after getting the clock frequency, the register is sampling the input data. So after sampling, the data is passed to self-timed logic. So DV is the valid data. I is the if you want to supply the new value. So through I, we will applying the new value here. This one is the interconnect circuit. So this circuit is helped to transmitting the data from one module to another module. So here we are passing 2 signals. So one signal is a acknowledgement signal and another one is a request signal. So this one is request signal. This one is acknowledgement signal. So module 1 is send request signal to access the module 2. So module 2 is giving the acknowledgement signal to access the module. So it's a handshaking signal. So here also DV is the valid data. So I represent for apply the input values. So this is the asynchronous interconnect block operation. So self-timed out logic. So after self-timed out logic, this output value is passed to register. So this register is sampled the data. Then again, the data is given to self-timed logic. So this is the simple explanation of asynchronous interconnect. Then come to the advantages of asynchronous interconnect. So the computations are performed at native speed of logic. So it's the first advantage. And second advantage is there is no need of manage clock skew. And third one, very modular approach where interaction between the blocks simply occur through handshaking procedure. So this handshaking protocol result increase the complexity and overhead in communication that can reduce performance. So these are the classifications of digital system signal. I hope you understand the concept very well. If you are watching first time in my video, kindly subscribe and support us to make a lot of videos. Thanks for watching my channel. Thank you. Connection last.